All right, so we've been talking about rates and how we can start to figure out for a given chemical reaction how quickly things are going to go from our reactants to our products. And so today we're going to be looking at how we start to express, or what we call our rate expressions. How we think about for a chemical reaction, we can start to describe how quickly our change is occurring. And that really is all we're doing. We're saying for a given reaction, a reaction rate by definition is a change in concentration in either your reactants or your products per unit of time. So if it's a really fast reaction, it might be in seconds or milliseconds. If it's a really slow reaction, it might be in years, if it's like a half-life or something like that. So here we've got just kind of our general reaction. We've got A changing into B. And so we're saying how quickly does A turn into B? That would be our rate expression. And it's expressed, it's going to be shared as kind of our change in concentration over time. Our reactants are going to get used up. Our reactants are going to decrease in concentration. Our products are getting formed. They're going to have an increase in concentration. And so we would say that our reactants are negatively changing. Our products are positively changing. And so if we wanted to mathematically show that, we're going to steal from physics here just a little bit. Our rate for our reactant is going to be a negative change in concentration. It is decreasing. It's kind of what that negative sign tells us. So it's the decrease in the change of concentration of A over the change in time, or more mathematically succinct, it's whatever your final concentration of A is minus your initial over final temp minus time, over final time minus initial time. Or if we want to actually use full physics symbols, that delta tells us the change. So it's the change in concentration of A over change of time, and negative because again, it's decreasing. For our substance B here, it would be the reverse of that. It'd just be the positive increase in concentration, but it's mathematically the same. It is a positive increase in concentration over our change in time. So it's change in concentration over change in time. Negative if it's reactant, positive if it is a product. And we can actually look at this graphically. We can actually measure some data and start to post that value and kind of plot that value. And so here, if we're still thinking A and B, right? Here we would say that our A is our kind of reactant. We had a lot of it at the beginning of the reaction, and we didn't have any product. That would be our blue line here. Product, we started with 0 moles per liter, or 0 molar of our product. And over time, A gets used up as B is forming. And so we're thinking about how quickly is this happening? And you'll notice a funny thing, the lines start to kind of even out or flatten out as we get a little bit later in the reaction. This makes sense. As you get less and less reactant, it gets harder for those particles to collide and to transfer their bonds. And so as a result, we see a decrease in reaction rate as we become less concentrated. And so if we're kind of thinking about our graphical data here, there's a couple different pieces we can pull off. If we took the tangent of the line right at the start, we would say that this is our initial rate. Here's how quickly this reaction goes right at the beginning of the reaction. If we picked any random points along the line and found the slope of that tangent line at that point, if we were to plot our tangent line slope, that would be rise over run. In this case, it would be change in concentration over change in time. That slope is our kind of rate calculation, change in concentration over change in time. If we took two spots at some particular point in time, we'd call those instantaneous rates. We said at this point in time, what is the instantaneous rate? How quickly is it changing based on the reaction? And if we go from start to kind of finish, we would call that our average rate from the total start to end of our experiment. And so thinking about our math here, oftentimes we could graph this, right? Yay, we could graph it and pull all these data points from the graph, but I don't know about you, but graphing can be a lot of work. And so oftentimes we'll just kind of take our values and we'll start to plug them in. So if we want to know for this particular reaction, I'm going to disappear for just a second here because I don't want to freeze on your screen. If we want to look for this particular reaction, mathematically speaking, we want to know the average rate. Well, our final for the average reaction was 60 seconds and we started at 0 seconds. And so it's change in concentration over change in time. Again, we're negative because our ozone is a reactant. So final minus initial, right? 1.10 times 10 to the negative fifth was our final concentration. Our initial concentration was 3.2 times 10 to the negative fifth. Sorry, ran out of room there a little bit. Negative fifth. That's going to be over the change in time. Final time was 60. Our initial time was 0.00. And we've got this whole value is going to be negative, which I think is just going to make our math work out. Because we have a smaller value subtracted by a larger value, this term comes out to be negative. This negative flips it back to a positive value. But if we think about what that means, so we plug in our math and we get a number, right? I think when we go about solving this, should be here on the next one here. I need to discard my writing. Yes, sorry, close this. When we actually do that math, we come out with a positive value, and that makes sense. Rate is going to be a positive number. You can't have like anti-time, right? Change in anti-time, inverse time. And so what that negative really means is that we are decreasing. For our ozone here, it is decreasing at a rate of 3.50 times 10 to the negative seventh moles per liter second on average over the course of the whole reaction. Here's how quickly our concentration changed over time. And that's what this value ultimately is going to tell us. But then that raises the question, what would that mean then for all of our other substances, right? We know how quickly our ozone is changing, but how quickly is our ethene changing? And how quickly is it forming just oxygen and this carbonyl carbon? There's got to be some way to relate that back to one another. And there is. Turns out it's our balanced chemical equation. Just to steal from this example, if it's all a 1-to-1 ratio, for every ozone that gets reacted, so does one ethene. In this case, this is a double bond here. This is a 1-to-1 ratio. For every one of these, we need one of these. So it would actually be the same rate for our ethene. And if this is how quickly this is getting used up, it's as equal to how quickly this is being made, because again, it's a 1-to-1 ratio. So those coefficients actually do play a part in our expression. So if we're thinking about a balanced chemical equation, just one in general, A and B, the capital letters here being the formulas of your compounds, the lowercase or red values here are the coefficients. We can actually use the coefficients to express our rates. And so we can actually say, if we're just thinking about how we would set these equal to one another, by dividing by their coefficient, essentially we change them back into a factor of 1, if you will, by dividing by that coefficient. And so it's 1 over the coefficient times its expression. These are negative because they are reactants. These are positive because they are products. And so by incorporating the coefficients, we actually can write these values as equal statements to one another. So we can actually transfer or calculate from one to the other how the rate expression will be. If we know one of them, we can figure out the other. So here's an example of that. So hydrogen gas, we use it for our space shuttles. Would also be great for our fuel cells. Could we actually figure out how we are changing with respect to time? Could we write the general expression, rate expressions, given this balanced equation? And then if we actually measure that here's how quickly the O2 is getting used up, could we figure out how quickly we would be making our water molecules? I think we can. And I think we just would incorporate our coefficients. And so if we're just thinking about our reactants, if we want to set them equal to each other, for our hydrogen, it's going to be negative 1/2. There's the 2. Change in the concentration of hydrogen. Remember, the brackets indicate molarity typically, over the change in time. That's going to be equal to, well, 1/1 is just 1. So it's going to be negative change in O2 concentration over the change in time. And all that's going to be equal to a positive 1/2 change in concentration of the water with respect to our change in time. So here are the rate expressions we've expressed. This is kind of letter A for us. Here is A. Well, that's a G. This is how we would actually express the rate for the changes in concentration over our change in time. Cool, but we actually know one of these, right? When O2 is decreasing at 0.23 moles per liter second, at what rate is the O2 increasing? Okay, so we've actually been given this value. We know it's decreasing, and there's kind of that negative piece, the decreasing. Our oxygen's decreasing at 0.23 moles per liter second. And that's gonna be equal to a positive 1/2 change in rate. So I'm gonna kind of group this so it's a little easier to think about. We wanna find this rate of our water formation. Sorry, I'm missing a bracket there. Cool. Okay, well, I think to solve this, we'd multiply both sides by 2, wouldn't we? To get this term by itself, the thing we're interested in. So we'd multiply by 2, 2 times 0.23, I think is gonna give us 0.46 moles per liter second. Now don't overthink this, guys. It was a 1 to 2 ratio, right? From the balanced equation. For every 1 oxygen you use, you make 2 waters. So it's going to be made twice as fast as we used up our oxygen. Just mathematically showing it with our expressions. But if we go back and think about our reaction, it makes sense that it would be formed twice as quickly as we used up our reactants. Cool. Just a quick overview on how we start to write our rate expressions. We look at some more examples here, but just wanted to give some to you to start to be thinking about.